we were studying the response of a first order system to sinusoids. Okay, and as usual we take this as the prototype, the first order RC, but exactly the same thing applies to anything else also. Now Vs, let's say, is Vp cos omega t. I mean, yesterday I had a plus phi in here, but that's okay, that's a detail, right? Now we identified a couple of possible ways of solving this. One is to write this as a sum of two complex exponentials, and because we have already solved the problem for an exponential input exponential st, we can get the answers to this. Okay. So what do we get if we do that? First, let's consider only this one, and also for now let's ignore the natural response. I'll tell you how to compute that later. Let's consider only the forced response. We know that this system, we have solved for this many times before. Exponential st, this gives you exponential st divided by 1 plus SCR, right? That is the forced response part, which we have already calculated. So the response to exponential j omega t we have Vp by 2 exponential j omega t, that is one part of the input. What would be the forced response to that? What is it? Vp by 2? Yeah, what is the scaling factor that we have? The same thing, right? All you do is substitute S with j omega. Okay. Similarly, Vp by 2 exponential minus j omega t, this gives you, all you have to do is to substitute S equals minus j omega. Okay. This is fine. And by linearity, the response to a sum of this and that is the sum of responses. So we have to add these two, right? And what do you get if you do that? And here we have that comes from these, and from the other one we get this exponential j omega t minus exponential minus j omega t. Okay. Now what is this? What is that? 2 times cos omega t. And what is this? Exponential j omega t minus exponential minus j omega t. What is that? J2 sine omega t. Okay. J of course is square root of minus 1. So, if you multiply this whole thing, we will get, and this factors of 2 cancel here. So, what we get is Vp cos omega t plus omega Cr times sin omega t divided by 1 plus omega Cr square. Is this correct? Okay, you get some combination of cos and sin as you had expected. And if you write this as a single sinusoid with some phase, I mean they are sinusoids at the same frequency, right? So, this can be written as cos of omega t plus some phase psi. What would that be? And also the amplitude will be different. Okay. So, please write it like that. What is this going to be? What is that? Minus tan inverse omega Cr is the phase. What is the amplitude? What is the amplitude of the resulting sinusoid? You sum cos omega t and omega Cr times sin omega t. What is the amplitude of the resulting sinusoid? Yeah. So, just the amplitude of this would be square root of 1 plus omega Cr square, and we will have cos omega t minus tan inverse omega Cr. Okay. So, the whole thing will be equal to Vp, the denominator we have square root of 1 plus omega Cr square, and we have cos omega t minus tan inverse omega Cr. Okay. So, the result is also a sinusoid at the same frequency. So, again I think a result known to you, if you have a linear time invariant system, if you feed in a sinusoid at a certain frequency, the output will be a sinusoid at exactly the same frequency. You cannot generate new frequencies using a linear time invariant system. Okay. But what happens is the amplitude of the sinusoid is different from what is at the input, and the phase of the sinusoid is also different from what is at the input. Okay. This sinusoid, the real sinusoid, this is not an eigenfunction of the linear system, right? This cannot be expressed as the input was cos omega t. This is not cos omega t times something. Okay. This has some other complications in it. Whereas for the exponential, complex exponential, adding a phase is simply like a scaling factor, right? If you have exponential j omega t and you add some phase exponential j omega t plus phi, what happens is that's like a multiplying factor of exponential j phi. Okay. So, an exponential is the eigenfunction of the linear system, sinusoid is not, but the output will be a sinusoid at the same frequency. Were you able to derive this answer or no? Okay. So, alternatively, we could recognize that when we have a differential equation like this, we guess that Vc would be of the form some linear combination of cos and sine, right? Because here we have the function and its derivative. If you have cos here, you get sine there. If you have sine here, you get cos there. So, to balance out and finally get cosine, you need both of them in general. Okay. And if you do this, you would have got Rc times the derivative, which is Rc minus alpha omega, sorry, sin omega t plus beta omega cos omega t. That's the derivative term, and Vc itself would be beta sin omega t plus alpha cos omega t. The whole thing should be equal to Vp cos omega t. Okay. So from this you see that alpha plus beta omega Cr or omega Rc should be equal to Vp, and minus alpha omega Cr plus beta equals 0. Okay. So this is the coefficient of sine, that's the coefficient of the cosine. Okay. And what's the value of alpha and beta you get from this? What is alpha? Yeah, I asked you to solve this, right? What is the value of alpha? What is it? Vp by 1 plus and beta is Vp times omega Cr, the same. Okay. It's very clear that you get exactly the same answer as before. The total will be this times cos omega t plus that times sin omega t, which gives you whatever we had earlier, right? Vp by square root 1 plus omega Cr square cos omega t minus tan inverse omega Cr. Okay. Obviously, I mean, it had better come out to be the same, otherwise we would be in trouble. So you can calculate force response in either way. You force response to a sinusoid, you express the sinusoid as sum of complex exponentials, or you beforehand guess that the solution itself is going to be a sum of a linear combination of sine and cos, and either way you have to find some constants and you do that. Okay. What do you do with the natural response? How do you get the natural response? How do we get the natural response here? I mean, we have calculated only the force response. What is that? Louder. No, whatever you say, at least I have to be able to hear it. Otherwise, how will I? What should I do? How should I calculate the natural response? Huh? Yeah, so we already know, I mean, Vp equal to 0 we have done, and we know the form of the natural response, right? So if you set Vp equal to 0, you get the homogeneous differential equation, and the solution to that is let's say this is some alpha n exponential minus t by rc. This we already know, right? This form we already know. Okay. So the total response is going to be Vp cos omega t minus tan inverse omega Cr divided by 1 plus omega Cr square under the square root plus alpha n exponential minus t by rc. This is Vc of t. Okay. So what do we do now? How do we find alpha n? Obviously, by setting the initial condition, right? Vc of 0 is Vp cos minus tan inverse omega Cr okay. So alpha n is simply this. Vc of 0 minus this whole stuff. Okay, and this is the way to account for initial conditions, because we are now adding the responses due to, let's say, two complex exponentials. You can't add the natural responses, right? So what I suggest is you compute the force response, and then after that you take the total response, and from the initial condition find the constant, multiplying constant for the natural response. Is this okay? I mean, if you take, let's say, the response to exponential j omega t with an initial condition Vc of 0, and the response to exponential minus j omega t also with an initial condition of Vc of 0, this is not, the sum of these is not the response to cos omega t with an initial condition of Vc of 0, right? You are adding up you are double counting that, isn't it? Yeah, that's right. Yeah. No, I know, but the initial condition is the same in the two cases, right? What will you do? So that's why don't even bother. I mean, why would you want to do that? Just compute the force response, and anyway, this is what you would have to do to calculate the coefficient of the natural response, right? Take into account the initial condition. That you can do afterwards. Then, yeah, I think it becomes the same. Yeah, I think so. I think then you can do that. Yeah, because the zero state responses are linear with the input, so that can be done. Okay. This is fine. So now again we have been like making our analysis more and more complicated. First we computed only the natural response of the first order system. It's exponential minus t divided by the time constant, and then we computed the force response to a constant input, then an exponential input, now a sinusoid. And for the sinusoid, we have two ways. One, to assume that the force response will be a linear combination of sine and cos, and the other one is to express the sinusoid as the sum of two complex exponentials. And because we have done the solution to the exponential earlier, we can write down the solutions. So which of these two is easier? Which one would you prefer to do? Or is there something even easier? We have two ways of calculating the force response to a sinusoid. Which is easier? Huh? Okay, why? But yeah, that's what, the same thing. I mean, cos and sine. The complex exponential you don't find as easy. Did any of you find the complex exponential stuff easier? Why? Okay, it's just a matter of personal taste. You can use whatever method you want. But there is an even easier method than this, which is what we use all the time. And this is something that is used widely, but even people who know how to use it properly have, or people who know it have difficulty explaining later how the whole thing comes about and so on. Okay. So let's again stick to force responses. Let's ignore the natural response. So let's say I have some linear system, just like my first order system. Okay. And to this I feed. I will also remove this Vp because everything is going to be proportional anyway, right? Whatever response I get, I can multiply that by Vp. I feed in cos omega t, okay? And this is what I wanted to calculate, right? The force response. So I don't know what it is, I'll just say y cos. Okay, that's the function. Y cos, this is the force response or steady state response to okay, whatever it is, it is. So this is what I want to calculate, but let me imagine that I have the same linear system, okay, and to that I feed sin omega t, okay, and the response will be something else, and I will call it y sin of t. This is the force response to sin omega t, okay. Then what? Of course, here also the next step is based on superposition. So, what is that? Okay. So, what I do is, this is a linear system, okay. Now, I feed, let us say, cos omega t plus j sin omega t to that, okay. What will be the force response here? Huh? What is that? It will be the same linear combination, right? Because I have a linear combination of inputs, I will have linear combination of outputs. Y cos plus j times y sin, okay. And this is the force response to cos omega t plus j sin omega t, which is basically the force response to exponential of j omega t. So far so good. I have a linear system with cos omega t as input, that gives me some response. I have the same linear system with sin omega t as input, that gives me another response. So if I take the same linear system and feed cos plus j sin, I will get the first response plus j times the second response. And of course, we know that cos omega t plus j sin omega t is nothing but exponential j omega t. So this y cos plus j y sin is the force response to exponential j omega t. Okay. So what next? Why did I do all this? Huh? 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 Yeah. So fine. Obviously, this in fact is easier than either of these, right? Because we've already solved for the force response of exponential st. So this one I can write more easily. Then what? That's not what I wanted, right? What I want is this. How do I get that? Take the, will that always work? What is the, you are saying take the real part of this, okay. So that gives me y cos. So what's the condition for that to be true? Huh? Y cos and y sin have to be real, that's correct. So in a general linear system, it may not be true. I mean, for instance, I can have a differential equation which is, let's say, j1 times dvc by dt plus vc equals vs, okay. But of course, we are now looking at circuits, that is basically linear systems with real valued components. So all the coefficients of a linear differential equation are also real, okay. So this is with real components, right. So this means that y cos is real as well as y sin is real. Okay. This won't be true for if you took some arbitrary linear system and I can make linear system with complex coefficients. I can just set it to be that way. But if I make a circuit with capacitors and inductors and resistors, this is not going to happen. Okay. So as long as I have components with real values, I will have only real coefficients. So in that case, y cos and y sin will themselves be real. Okay. So what I can do is compute the response to exponential j omega t and take the real part. Okay. So would this be easier than the other two or no? Definitely easier, right? Because the first one, when you decompose it into two exponentials, you are doing the same thing in twice. Why bother? You can just do it in one step. Okay. So the force response to cos omega t, this is the real part of force response to exponential j omega t. Okay. We have, this is by the way not only true for first order systems, this is for anything. Okay. Because I just said linear system, it can be anything. This is okay? So again, let's take this, the same system. Okay. What is the force response to exponential j omega t of this? This is the equation for the first order RC circuit, right? What is it? Yeah. So for exponential st, it was exponential st 1 by 1 plus SCR. Here it is exponential j omega t 1 by 1 plus j omega CR. Okay. What is this thing that is multiplying this? I called it something, right? This is the transfer function h of s. Okay. So here what we get is exponential j omega t times h of j omega. Okay. This s equals j omega business you must have done many times, right? For various reasons. Basically, this is what it is, to compute the response to a complex exponential. Okay. S equals j omega corresponds to cos omega t plus j sin omega t. Okay. And then you have to take the real part of this. How do you do that? It's quite easy. I mean, you can rationalize this 1 by 1 plus j omega CR. This is equal to 1 minus j omega CR divided by 1 plus omega CR square, and you multiply this with that, and you can take the real part. Okay. Is there an even easier way? I mean, of representing the complex transfer function slightly differently. What are the different representations of a complex number that you know? Huh? Polar form. What is the polar form of this? 1 over 1 plus j omega CR. You can have or the amplitude and phase, right? So 1 by 1 plus j omega CR, this is h of j omega. What is the amplitude? 1. 1 by root of 1 plus omega CR square, and the phase exponential minus j. What is the phase? Not omega CR, tan inverse of omega CR, right? Minus j tan inverse of omega CR, isn't it? Is that fine? So this is the easiest way, right? Because h of j omega times exponential j omega t will be the amplitude 1 by the magnitude 1 by 1 plus omega CR square under the square root exponential minus j tan inverse omega CR times exponential j omega t. Okay. So these two will combine to give you exponential j omega t minus j tan inverse omega CR. And what's the real part of this? Whatever is the argument of the complex exponential, that goes into the cosine, that's all. So real part of this will be okay. So it can be straightforwardly written down. Essentially, the transfer function is what multiplies the complex exponential, right? So if you write the transfer function in its polar form, that is the magnitude of the transfer function and the phase of the transfer function, what happens is the amplitude of the input sinusoid gets multiplied by the magnitude of the transfer function, and the phase of the sinusoid gets shifted by the phase of the transfer function. That is all that is happening, right? Okay. So again, so in general, of a linear force response of a linear system to Vp exponential St is some transfer function h of s times Vp exponential St, right? This we know. So the force response of a linear system to Vp exponential j omega t is h of j omega, that is the transfer function evaluated on the imaginary axis. I think I have done these things already with the Laplace transform. Vp exponential j omega t, and the force response of a linear system to Vp cos omega t, what is this? This is the real part of h of j omega Vp exponential j omega t. Okay. The easiest way to see this is if you write h of j omega as the magnitude of h of j omega times exponential j angle of h of j omega, right. So, what we will have here is real part of Vp times the magnitude of h of j omega, that is a real number, and exponential j omega t plus j angle of h of j omega. Okay. And what is that? That is simply Vp magnitude of h of j omega, and the real part of this is nothing but cos with the same argument, right. Okay. So, you will have cos omega t, the same thing there, but the amplitude will be changed and the phase will be changed. Okay. So, actually extremely important result both for analysis and for measurements and so on. The fact that if you feed a sinusoid to a linear system, what comes out is a sinusoid at the same frequency. Its magnitude can be changed, its phase can be changed, but it is still a sinusoid. This is not true for any other signal. If you feed a square wave to a linear system, you are not going to get a square wave, you will get something else. Okay. So, the point of all this is that you do not even have to go through those steps that we did earlier, right. Meaning, you do not have to sit and write exponential j omega t, find this and take the real part and so on. All you need to do is you have to calculate the transfer function. Okay. Once you have calculated the transfer function h of s or h of j omega, if you feed in a sinusoid at frequency omega, you look at the value of h at the value at the point j omega. Okay. It is a complex number, or it has some amplitude and some phase. So, its amplitude will modify the amplitude of the input sinusoid, its phase will get added to the phase of the input sinusoid, that is all. Okay. So, all you need to do is find the transfer function to find the force response to a sinusoid. Okay. So, this is what makes it easy and manageable for more and more complex systems, right. Because if you sit and write let us say the whatever variable you have as alpha cos omega t plus beta sin omega t for a fifth order system, you will have to solve for so many things, it is a pain. I mean, you have to solve for two constants, but it is a cumbersome thing to do. This part I assume you knew, that if you have a sinusoid going through a linear system, its amplitude gets modified by the magnitude of the transfer function and its phase gets shifted by the phase of the transfer function, right. This is something that is known or no? No? So, what did you do with the Laplace transform? No, I mean, we have all these things for a reason, right? They are all tools for solving something, that is all. So, this is very important because we use exponential j omega t in calculations everywhere. In fact, if you go to the communications guys, I mean, you will not find cos omega t anywhere in the textbook, you will have only exponential. But all this also relates to something we do in the lab. What is J in the lab? There is no, I do not have imaginary signals in the lab. Okay. So, finally, I feed sinusoids to some system and I want to figure out what comes out. Okay. What is that? This business of using exponential j omega t is, at least in this context, it is easy for analysis. What I want is a response to cos omega t. So, it is easy to analyze it by feeding exponential j omega t, looking at the response and taking the real part. What it means in practice is, if I have the transfer function of some system, if I feed in a sinusoid and wait for the system to reach steady state, okay. So, let us say I have a linear system where transfer function h of s and I feed, let us say, Vp cos omega t and out comes something. Okay. What is that? If I feed both of these to an oscilloscope, okay. So, let us say Vp cos omega t, it looks like that, or maybe let me draw more than one cycle of it. What comes out will be something else, okay. and if the amplitude of this is Vp, the amplitude of that will be h of j omega times Vp. And what is this omega? This omega is the frequency of the sinusoid that you have applied. Okay. In fact, the moment you apply the sinusoid, you will have the natural response of the system also. If we assume that the system is stable, that will die out after some time, and what persists is the force response or the steady state response. So you should see a sinusoid. Okay. And similarly, this will have some phase difference. Okay. So between this peak and that peak, there is some phase difference. So that is nothing but the angle of, okay. And we know the expression also, the output is nothing but Vp times this and cross of omega t plus angle of h of j omega. So if you know h of s for all frequencies, you can find the force response to any sinusoids of any frequency. Okay. Is this okay? And you combine this with any signal can be represented as sum of sinusoids. Okay. So you find the response to any signal now. Okay. Square wave also you can find. What you have to do is take harmonic by harmonic. A square wave, a symmetrical square wave has the fundamental and odd harmonics. So you find h of, let's say your omega is 1 radian per second. So you find h of j1, you look at what it does to the first harmonic, h of j3 that does something to the third harmonic, h of j5 that does something to the fifth harmonic, and you can add up all the results. The result may be simple or complicated, you may or may not be able to express that in a nice closed form, but that's the result, you can compute it. Okay. So this way the study of the analysis of linear systems is very easy. What makes it easy is linearity and superposition, right? So you can take any complex signal and you can break it down into some set of convenient signals. One convenient set of signals is set of sinusoids. Okay, they are orthogonal basis functions for representing signals, but you could do it in some other ways also. Okay, because superposition is valid, what you do is you analyze the linear system for each of these constituent signals separately and then add them up in the right proportion. Okay. Any questions so far? So this is where all the transfer function business comes from. So let's say I applied Vp sin omega t. What would you do? What is that? Imaginary part. You could do that, but don't do it. I mean, just stick with cos as a reference. Any signal you have, this is that, okay? Or any signal that you have, you simply refer it to cos with the appropriate phase, okay? So if you do that, the response will also be, that phi will simply get added here, that's all, okay? So stick to the real part and do it this way. There is nothing wrong with that, but it should probably get confusing if you start doing that. Is this okay? So complex numbers are great. There are many nice properties that you can exploit while analyzing many things, and you do it all the time in electrical engineering. There is no modern electrical engineering without complex numbers. Okay. But of course, finally the result ties to some real signals in the lab and so on. So this is what happens. Okay. So the transfer function itself is a complex number. What is that telling you? That is telling you how a complex exponential gets multiplied when it goes through a linear system. And why complex exponential? We use it. One of the, a practical viewpoint would be the calculating the response to cos omega t is a lot more complicated than doing it for exponential j omega t. And from exponential j omega t, I can very easily get the response to cos omega t. So that's why I do this. This is the analysis viewpoint, right? And finally, you don't even have to go through the intermediate steps of, oh, I have an input of exponential j omega t, this is what this gives me, I take the real part of that and so on, okay. All you do is, you characterize this system with its transfer function h of j omega, then if the input is 1 volt, the output will be 1 volt times the magnitude of the transfer function at that frequency, and if the input has, let's say, some phase of 45 degrees with respect to cos, the output phase will be 45 degrees plus the phase of the transfer function at that frequency. Okay. So, that is all you have to do. So, that is the utility of the transfer function. Okay. And once you have the form of the, once you have the forced response, it is easy to find the natural response. You know the form of the natural response already, right, that you know from the homogeneous differential equation. Okay. For the first order case, it is exponential minus t by RC or minus t by tau, whatever it is. So, all you have to do is to find that one constant that you can do by relating it to the initial condition. Okay. If you have a higher order system, you will have more than one constant, but you also have more than one initial condition. The number of initial conditions and the number of constants is the same as the order, and you can find all of them through a bunch of simultaneous equations. Okay. Why are sinusoids used in measurement? I mean, you have been to the lab, you have seen signal generators, they generate variety of signals, but I will tell you that the sinusoids are the ones that are most frequently used for measurement. Why is that? Yeah, so what? Any signal can, what did you say? Any signal can be represented as? Yeah, but why bother taking the sum if I can just apply the signal directly? Huh? Yeah, I know, but what is the utility of that? Huh? What is that? I heard some answer here. Maybe, but anyway, that's not the. What is that? Okay. I mean, sinusoid has many utilities. Basically, sinusoids are, sinusoids are different, of different frequencies are orthogonal to each other. So, they form, basically that is what you are saying. They form an orthogonal basis for representing other signals and so on. But just imagine a lab setup. You have the signal generator, okay, and let us say you have your device under test, commonly called a DUT, okay. Let us say you have the oscilloscope or some analysis instrument, it could be a spectrum analyzer, it could be an oscilloscope, anything, okay. Now, this generates and sometimes this device under test will be embedded inside other circuits and so on, okay. But let me just consider wires connecting these things, okay. Now, these wires are not perfect, okay. They themselves will have, at the very least, if you, let us say you think of a pair of wires, okay, they will at least have some resistance and some capacitance. So, the wire by itself is some system whose transfer function is not 1, okay. But at least we can reasonably rely on it to be linear. That is, if you do not pass very high currents or if you do not apply very high voltages, it will be linear. Now, what happens is that, imagine, like, what would happen if you apply a square wave to this? What will you get here? Yeah, it will, you may have calculated it, it will look some rounded off stuff like that, and the exact details will depend on the values of R and C, the frequency of the square wave, and what is actually here and things like that. But this is where the sinusoids, giving sinusoids is valuable. If you have a sinusoid here or here, let us say, you will have the sinusoid with the same frequency. Its amplitude may be different, that is fine. Here you apply 1 volt and here you may only get 0.8 volts or something, okay. But it will still be a sinusoid. And similarly, if the output is expected to be a sinusoid, it reaches the scope maybe with some attenuation. Maybe if the device gives out 2 volts, this will only read 1.8 volts, but it will still be a sinusoid. And there are ways of calibrating for the loss that appears here, okay. For instance, first before I do anything, I connect this wire to that wire directly, and if I set 2 volts here, I will see what comes out there. So, that will be the magnitude of the transfer function, right. So, when I connect it here, I also know that maybe it will get reduced by 20%. So, I take that into account and so on. So this is why again sinusoids are very useful. This doesn't mean that you don't use other signals for characterizing. Sometimes you may be explicitly required to characterize a signal with a pulse and so on. But the arrangements that you need to make are a lot more stringent. That is, you have to make sure that you use the right wire that doesn't attenuate the pulse. Of course, will have all harmonics up to infinity. There is no real system that will support all those harmonics, but at least you should have enough harmonics so that the square pulse looks like a square pulse and so on. Okay. So it is simply a lot easier to do things with a sinusoid than with any other signal. So that's why they are most widely used. Again, you use all kinds of other signals, but this is the most basic one. Okay. And there are very good reasons to use that for analysis as well, as we have seen. And we can represent any signal as a sum of sinusoids through the Fourier series or the Fourier transform. So that's why the sinusoid is the signal of choice. Okay. But please think about these things. Anything that I derive in class, please rederive it, and then only then you will have a good understanding of what's going on.